Hey there, in this video I'm going to talk about how dropouts can reduce the underfitting in underfitting models. In the future we will have the quintillion bytes of data, and we will be not be able to process that data. The models we are going to build is going to be too small to generalize on that data, so our models are going to underfit. So this early dropouts can be effective there, and it can reduce the underfitting to significant extent. During the initial approaches of the optimization, we all know that the gradient updates, they are very crazy, and they are very unstable too. So what it means is the gradients are very noisy. It is because our model has started to generalize on the some data, and so it is producing huge gradient variance in both direction and in terms of optimization too. So to reduce this, the dropouts was used. So dropout is reducing the complexity of the model, and it is dropping some particular nodes at a particular time during a epoch. So this way, the complexity of model decreases and the variance is reduced. So the variance in terms of a direction and also in the parameter space, the both of them are reduced. So this way, the earlier the Adam was taking very long strides, but it was having the wrong direction. So after using the early dropouts, the strides are shortened, but they are just in consistent direction. So it can be quite analogous to a drunkard man walking in the park. He reaches the home after 4 or 5 hours, but there is one person who is just taking the smaller strides, but he reaches the home in just 30 minutes. So it is quite analogous to this. So in short, it is like smoothing of Adam updates during initial approaches. So it will be more clear if you watch the video ahead. I think this diagram is suitable to explain the most of the concepts related to the neural network optimization. As we all know, this optimization process is non-convex. So our optimization is prone to local optima and saddle points. So to begin with batch gradient descent, in batch gradient descent, the gradients are computed based on the all the data points. So this way, our optimization is process is very smooth. No doubt it has more memory overhead, and it takes huge computational resources, but our optimization process is very smooth. So this way it will always converge to the optimum point. But this is prone to some saddle points and local optima and all that. And the second is the stochastic gradient descent. In stochastic gradient descent, the only one data point is forward propagated, and during the back propagation the gradients are computed on the single data point. So this way, we have less approximation of the entire data, and this that is why the gradients are very unstable, and our optimization process is not very smooth. But due to the randomness, so this doesn't get stuck into saddle points and some local optima. So this is why this is somewhat better than this batch gradient descent. And the third one is mini batch gradient descent. In mini batch gradient descent, we divide the entire huge data set into some batches, and during and the that batch is forward propagated, and during the back propagation the gradients are computed. So this way, it has a better approximation than the stochastic gradient descent of entire data, and the gradients are way better. So this has a better optimization, and it converges to a better optimum solution. So the third is the Adam is it mini batch based gradient descent method, but it also takes momentum and exponentially decaying learning rate. So intuitively what it does is it will have the better approximation of this mini batch, and it smooths the mini batch gradient descent, and finally our it reduces the underfitting, and our solution is way better. So but this is more computationally complex because momentum is also used, and was a high level intuition of the optimization. So now let's jump to the paper, and I will explain like how dropouts are even assisting the ADAM in optimization process. Now let's talk about ADAM briefly. Like ADAM is mini batch gradient descent, so it is also taking momentum based approaches to like smoothing the gradient updates, and also it has some exponential decaying learning rate. So that is why like what ADAM is doing is like the instead of like this unstable gradient update, so it is like smoothing the optimization process. So what the dropout is doing is like it is reducing the directional variance even more, and also it is reducing the gradient update magnitude significantly. So what it means is like now with the early dropouts, the magnitude of the gradient updates is smaller, but the direction is right. So it is like quite analogous to like one person who is walking in the right direction, but he is taking the smaller strides, and he is able to reach the home earlier than the other person who is just walking with the longer strides randomly. So this is how dropouts is just helping over here. So now let's jump to the results section. Now let's discuss about this diagram, which can even consolidate our understanding. So it is like quite noticeable from here, like there are two models. So one is a baseline without a dropout, and the other one is with dropouts. So what the model with the dropout is doing is like it is producing like a less gradient norm. Less gradient norm means less magnitude of the gradient. So the model distance is more in the multidimensional parameter space, so it is like quite noticeable. It means like no doubt having the smaller steps, but it is moving in the right direction. So the model is like our optimizer is converging better. This diagram is also explaining the same finding. So it is like quite noticeable over here, like the gradient directional variance like is very less in while using the dropouts for some early approaches. So like it is like very significant. It means like the variance of a directional gradient update is very less in initial approaches. Similarly, the gradient directional error is also very less when we are using a dropout for early approaches. So it means like when we are using the dropouts for the initial approaches, this angle is reduced, so it is like correcting the direction for some initial approaches. Researchers have even done the further analysis. So it is like quite clear from here, like the early dropout is like it is effective with wide range of dropout approaches. Like when the number of approaches are considerable, so they are neither too high neither they are too less, so the early dropout is like producing the better results. So similarly, early dropout is like best producing the best result as compared to the increasing dropout and decreasing dropout and some other even complex operations. From here it is also quite clear that early dropout is like producing better results whenever we have like a less dropout rate. I would say like a dropout rate less than 0.35. So early dropout is producing better results. Also, early dropout is also effective when we have a different learning rate warm up schedules. Like whenever we are giving 20 approaches for the warm up, it is also producing better results, and whenever like we are giving 100 approaches, so no doubt the results are considerably very less as like, but they are like consistent with the earlier finding. So it means intuitively like whenever like learning rate warm up approaches are considerably less, so early dropout is still effective, but the early dropout is not effective whenever the batch sizes are too large. So if the batch size is 8192, then early dropout is like producing the similar results as the baseline. and it is like quite noticeable from here, like whenever the early dropout ends, so there is increase in the accuracy and there is a decrease in loss, like because we have like more and more layer connected and the complexity of model increase and the understanding of the model increases too. So like it is learning better, so that's why accuracy has improved. To conclude, I would like to say early dropouts are effective whenever our models are underfitting. So what it means is like when we have huge quintillion bytes of data and the complexity of model is not like very less as compared to that. So then the model is going to overfit. So early dropouts can be used over there to reduce the underfitting. So whenever like the model is overfitting, we have less data and the model complexity is more, then the late dropouts are effective. In this, all the work was done on image dataset and the model used was vision transformers. So it needs to be further evaluated and tested, like whether this is working on NLP problems or even it's working with the different models, like with different deductive biases like CNN, or there are 3 or 4 different kind of attention mechanism, like causal attention, mask self attention, and linear attention is also there, which relies on low rank matrix factorization. So it needs to be further evaluated and tested, like whether the early dropouts and late dropouts, they are consistent with all the different models or not. So that was all I have to say. Thank you, thanks for the listening.